Chapter 3, Polynomial and Rational Functions, Section 3.3, Polynomial Division. We're going to see that polynomial division plays an important role in working with polynomials, in factoring polynomials, in finding zeros of polynomials, or, if you prefer, in finding solutions of polynomial equations. So we'll begin with a study of just the division process or algorithm in general, and look at it from 2 points of view: the point of view of long division and then synthetic division, which can be used in certain cases and is a shortcut. Long division with polynomials is very similar to what we do with whole numbers. So we're going to illustrate this just with a very simple example, and this is not done to insult your intelligence, but to show you the connection between what you already know about long division with whole numbers and how long division with polynomials works. So suppose we wanted to do 87 divided by 5. All right, so we might set it up like this: 87 divided by 5, and then we say, okay, well, how many times does 5 go into 8? One time. Okay, now at this point we multiply. 1 times 5 is 5. Then we're going to subtract. 8 minus 5 is 3. Then we're going to carry the next digit down. That would be the 7. And then the process repeats. We ask, how many times does 5 divide into 37? And it, or how many times does 5 go into 37? Maybe I should say 7 times. Then we multiply. 7 times 5 is 35. Then we subtract again. 37 minus 35 is 2. So notice there's a process of multiplication and subtraction when we do long division with whole numbers. Now, the numbers we've obtained here have special names. First of all, the given number 5 is called the divisor. The number on the top, which is the main result of the division, telling us how many times 5 divides into 87, 17 times, then that's called the quotient. And then the 2 at the bottom, which is a little bit of leftover after doing the division. That is the remainder. And then we can write the result. Of course, we could just write it like this, but we could also summarize the result a couple of other ways. One way would be to say, if we take 87 divided by 5, but write that like a fraction, 87 over 5. You know, any fraction is a division. So if you write 87 fifths, that's 87 divided by 5. So we say that is the quotient, and then the remainder over the divisor, 17 and 2 fifths. And of course you would recognize this as a method of converting an improper fraction to a mixed number. Now 17 and 2 fifths is really 17 plus 2 fifths. But we don't write the plus sign. It's understood that the 17 and the 2 fifths are actually being added. With polynomials, when you write the results, you have to explicitly show the addition. So I'm just showing it to you here, not because we write it this way with whole numbers, but because it is understood to be an addition. The second way we could express our result would be to say that 87 is equal to the divisor, 5, times the quotient, 17, plus the remainder, 2. 5 times 17 plus 2. And of course, this is a way we could write a result as a way of checking that our division has been done correctly. So we do 5 times 17, which should be 85, then add 2 to get 87, and it checks out. With polynomials, this is an especially useful way of writing our result because it indicates whether or not the polynomial has been factored. The fact that we have the sum of 2 on the end in this case means 87 has not been factored using 5 and 17. We would not say that 5 and 17 divide evenly into 87, of course. So now the process we've seen of division with whole numbers carries over to polynomials. And the procedure or algorithm for division with polynomials is summarized by the division algorithm. And this is patterned directly out after whole number division. If the polynomial f of x is divided by the divisor d of x of degree less than or equal to f of x, we obtain a quotient q of x and a remainder r of x, where r of x equals 0 or the degree of r of x is less than the degree of d of x, such that we may write f of x over d of x, or f of x divided by d of x, equals quotient plus remainder over divisor. Or in a second way of writing it, f of x equals divisor times quotient plus remainder. So these are the two ways of summarizing the division, just as we did with the whole number example a moment ago. Notice that instead of talking about one number being bigger than or smaller than another number, here we talk about the degree. We compare degrees in determining what we are allowed to divide by and when the division process stops. In this case, the division process stops when the degree of the remainder is less than the degree of the divisor. If the remainder r of x is 0, then the divisor and quotient d of x and q of x are called factors of f of x, and we say f of x factors as f of x equals d of x times q of x. This is just based on the result that you see here above, but the r of x is 0, so we just get d of x times q of x. We've written f of x as a product of polynomials of usually lower degree. This is something that we will need to try to do to solve polynomial equations. Let's now see how the division process actually works with a specific example of division. Perform the indicated division in example 1 and express the result in the forms described by the division algorithm. So in part A, we want to divide f of x equals x squared minus 3x plus 11 by the divisor d of x equals x minus 2. And the way we'll set this up is we'll put x squared minus 3x plus 11 here, then a division bar and the divisor here, just like you would with whole numbers. Now, what determines what we put in the quotient, the idea is we want to multiply x here by something that will give us the first term here. And that's what we put in the quotient, and that would have to be x. X times x is x squared. Then the x also multiplies the negative 2. So it multiplies the x and it multiplies the negative 2. So that goes below the minus 3x. Then, just as we do with whole numbers, we subtract. X squared minus x squared is 0. Minus 3x minus 2x is minus 1x or minus x. This is the one step in long division where people tend to make mistakes. And that is, instead of subtracting, they add and get negative 5x here. Now, a way to avoid this is prior to determining what number or what term to put down there at the bottom, change the signs here. You have to keep in mind, however, that the signs that you're changing over to are opposite what they were originally. So if you're checking your work, you have to keep that in mind. But when you change the signs, then you can add, and then it's easier. So negative 3x plus 2x is minus 1x. So that's something you can consider doing if you wish. But it's really a subtraction. And then just as with whole numbers, we would bring the next digit down. Here we bring the next term down, 11. Then we ask, what should we multiply x by now to get minus 1x? That would have to be minus 1. You put that in the quotient. Then you multiply negative 1 by both the x and the minus 2. Minus 1 times x is minus 1x. That should match up exactly. Negative 1 times negative 2 is positive 2. The minus 1x cancels the minus 1x above it, and 2 is subtracted from 11 to give 9. Here it's easy to see 11 minus 2 is 9, so I won't change any signs here. And then how might we express our result? So one way would be to say that if we take f of x, x squared minus 3x plus 11, and divide by x minus 2, writing it as a fraction, then the quotient is x minus 1. So this is q of x. Then we add to that the remainder, which is 9. So 9 is r of x over the original divisor, which is x minus 2. This is analogous to writing an improper fraction as a mixed number with whole numbers. A second way to write our result would be to say that f of x, that is x squared minus 3x plus 11, is equal to the divisor, x minus 2, times the quotient, x minus 1, plus the remainder, which is 9. Again, this actually is a more useful way of writing the result. It indicates that the polynomial has not been factored completely because it's not expressed merely as a product, but as a product and a sum. We can also use this way of writing the result as a check on our work. So if we look at the product, oh, excuse me, just a moment, please. Okay, I'm back now, and if we multiply by FOIL, x minus 2 times x minus 1, we get x squared minus 1x minus 2x plus 2, or x squared minus 3x plus 2. If we add 9 to that, we have x squared minus 3x plus 11. So by writing it this way, we have a check on our division to know that it's been done correctly. So that's how the division process works, the division algorithm for polynomials. And we need to look at one more example, and then we'll look at a shortcut which can often be used in place of long division, which is synthetic division. So we'll continue that in the next video.